Well, a warm welcome to everyone and thank you for joining the webinar. My name's Dave Marshall-George and I'm the UK and Ireland Sales Director for Condair. And with me is Anthony Hall. Anthony's the Area Sales Manager covering the Midlands here in the UK. We've over 400 people joining us today from 49 different countries across the world. So on the call today, everybody will be on mute. If you have any questions, please submit them using the text question function in the control panel. And we'll answer some as we go, but when the presentation is finished in about 45 minutes, I'll also be addressing some of the most popular questions before we conclude. I'd like to draw your attention to the 3 documents available for download in the control panel. There's the presentation in PDF format. There's a psychrometric chart and Condair's air handling unit cooling brochure. After the webinar, all attendees will receive a link from which you can download a CPD certificate. And as a brief introduction to Condair, we're a privately owned company with over 700 staff with our head office in Switzerland. And I've been a world-leading producer of humidity control equipment for over 70 years. And we manufacture in Hamburg, Ottawa, Beijing, and we export globally. Right, I'm going to turn my camera off now and we'll proceed with the presentation. So firstly, again, thank you for joining us today. The webinar today is about using air humidifiers for evaporative cooling in air handling units. And the objectives for today are that we're going to look at the physics and benefits of evaporative cooling. Then we're going to look at evaporative cooling strategies in air handling units. First of all, we're going to look at direct evaporative cooling, then indirect evaporative cooling, and then exhaust air indirect evaporative cooling. Now, for each of these strategies, we're going to look at a live case study so you can understand how each process works and the energy savings that have been experienced by using these strategies. And then after that, we're going to take a look at different evaporative cooler technologies and the pros and cons of applying them. And then finally, a brief mention of some online tools. So when we dive into the physics and benefits of air handling unit evaporative cooling, what are we actually doing? Well, effectively, we are evaporating water in an airflow. And when we evaporate water, we are changing the state of a liquid. In this case, the liquid being water, and we're changing its state from its liquid phase into its gaseous phase. And whenever you change the state of a liquid, that requires energy. And of course, the only energy source available to us here is heat energy. So as the water changes its state from its liquid phase into its gaseous phase, heat energy is taken out of the air and transferred into the liquid. So the net effect is that we reduce the air temperature. So the huge benefit here is the low energy consumption because we're just relying on physics. We're just evaporating water into the air and sucking heat energy out of the air and utilizing that cooling. So we're not using any mechanical equipment here. We're not using a compressor. We're not using an oil management system. We're not using all of these things that would traditionally go into a direct expansion refrigeration system. We're not using a chiller or anything like that. All we're doing is evaporating water into the airflow. And to give you an idea of the amount of cooling that's available, you can get up to 680 watts of cooling or these 680 watts of cooling is required to change the state of 1 kilogram of water. So you can work it out for yourself. If you evaporate 100 litres of water into an airflow, you get the subsequent amount of cooling. Now, there's no such thing as a free lunch. Of course, air needs an initial low humidity to allow moisture to evaporate and therefore provide cooling. Because we know that air can only hold so much water. So if the air is already saturated, then our cooling potential is reduced. So what does this look like psychrometrically to really understand the process of evaporative cooling? I'm sure many of you are familiar with the psychrometric chart. I'm just going to run through the basic elements here. At the bottom of the chart, we have the dry bulb temperature, starting at -10 and going up to 60 degrees C. Next, we have the wet bulb temperature, and that's going diagonally along the chart. There's 15 degrees C wet bulb, 16, 17, there's 20 degrees C wet bulb, 25. And from these two temperatures, we can derive several other factors. So if we are at 20 degrees C dry bulb and 14 degrees C wet bulb, we'll see that we're at 50% relative humidity. So we can read our relative humidity right up the chart. There's 10% relative humidity, 20%, 30%, 40, 50, and so up until we get to saturation point or dew point. So we have dry bulb temperature, wet bulb temperature, relative humidity. We also have the absolute moisture content, in this chart shown in kilograms per kilogram of dry air, running up the chart. And we also have the specific volume shown in meters cubed per kilogram, and it's about a 70-degree angle down the chart. There's 0.85, 0.86, 0.87 meters cubed per kilogram. And finally, we have the specific enthalpy, which we can read from the table that surrounds the chart. And we're going to look at this table here and the bottom table. And when we plot the specific enthalpy, we take our dry bulb temperature and either our relative humidity or moisture content or wet bulb temperature, and that gives us a plotting point on the chart. So we take our point and then we draw a line from this scale down to the bottom scale in the chart. And that will tell us the specific enthalpy. Now, specific enthalpy is really important for us in the psychrometric process of evaporative cooling. So here we're drawing the line of specific enthalpy from a point of 40 degrees C at 10% RH. As we follow the line of enthalpy, we see that we get a decrease in dry bulb temperature, we get an increase in moisture content, and an increase in relative humidity. You can see we've gone from 10% RH, 20, 30, 40. As we're evaporating water into the air, we're changing its state from a gas, from a liquid into a gas. We're increasing the relative humidity. So our relative humidity is increasing. Our moisture content is increasing. You would expect that because we are putting moisture into the air. But our dry bulb temperature, of course, is decreasing, and this is the critical factor that we want to utilize. Now, importantly, this line of enthalpy that we've drawn from this scale, intersecting our condition down to the bottom scale, it does not follow the wet bulb temperature line. It follows the line of enthalpy. They are very subtly different. So this is the key thing that we're doing when we're evaporatively cooling. We're taking air that has the ability to accept more moisture into it. We're evaporating that water into the air. We're seeing an increase in relative humidity. So there's 10, 20, 30, 40, 50, and so on. We're seeing an increase in moisture content, and we're seeing a subsequent decrease in dry bulb temperature. Now, we did mention on the previous slide that, of course, the air has to have the ability to receive this moisture. And you can see on the chart, if your start condition has a high relative humidity, if you're at, let's say, 20 degrees C and 80%, well, clearly, you're not going to be able to evaporate much moisture into the air. So this we'll then have to look at different air handling unit strategies to see how we counteract that. So now we're going to take a look at the different different air handling unit strategies for evaporative cooling. And the first one that we're going to look at is direct evaporative cooling. Now here we are taking fresh outdoor air, and in this model we're running that through a filter first, and then we're evaporating water into the air. So we're getting the subsequent increase in relative humidity, increase in moisture content, decrease in dry bulb temperature. So we're cooling the air as we're using that heat energy to evaporate water into the air. So we're then sending that cooled, humidified air into the space. And then return air comes from the space and is just exhausted. It's the most simple form of evaporative cooling. It's purely direct evaporative cooling. So next, let's take a look at an application that delivers this sort of a system. And when we look at the application, you'll be able to see that the benefits, of course, we can deliver a high volume of cooling. Again, 680 watts per litre of water that we're evaporating. It's also going to provide potential for humidification in the winter because we are actually putting moisture into the airstream, and it's ideal for hot climates. So our case study, this system was developed by an air handling unit manufacturer in the UK called Weatherite, and the objective was to replace existing compressor-driven cooling systems with a refrigerant-free, energy-efficient solution for all low to medium heat density telecom rooms throughout the UK for a leading telecoms provider. So first of all, one of the design criteria was that it had to fit in the existing footprint of legacy equipment. So the legacy cooling equipment was DX, and this system had to be designed to take one out and put one in. And they wanted to use evaporative cooling, but of course, evaporative cooling isn't always required. You can do a tremendous amount of cooling with fresh air. So how this system works is that at the top of the unit here, we've got circulating air that can either be circulated back through the unit and out back into the space, or it can be diverted off to be exhausted. And when we can satisfy a cooling demand with either circulating air or fresh air or a mixture of the two, air will come from the rear of the unit, go through a filter, a bypass damper will open at the bottom of the unit, and that fresh air and circulating air will mix and will be supplied into the space. And you can see that there's the supply air grill at the bottom of the unit. What you can see in the picture on the left-hand side, inside the unit, is the glass fibre evaporative matrix that is brought into play when cooling is required, or evaporative cooling is required. When evaporative cooling is required, hence we can't satisfy the cooling demand with purely fresh air, we then go into mode 2 evaporation, where adiabatic cooling is required. And at this condition, the bypass damper will close, and that forces air through the evaporative media. Water is evaporated, so we see the subsequent reduction in air temperature, increase in relative humidity, increase in moisture content, and that, if it's required, can be mixed with circulating air and then goes down to the bottom of the unit and then is supplied out. So we get evaporatively cooled air going into the space. So it's very simple in its design, and all we're doing is we're evaporating water off, in this case, a glass fibre porous material, where water is constantly replenished from a tank at the bottom of the unit and pumped up to the top of the unit. So the unit is constantly has water cascading over the glass fibre matrix. So what about performance? What does this actually do for the client? Well, there's a lot of data on this slide, so I'll just try and break it down into columns at first. If you draw your eye to the left-hand side of the table, you can see the ambient temperature listed in degrees C. And it starts at -5 and then goes up to 35 degrees C. The next column that you can see shows the hours per year that we experience these ambient temperatures. So then we can plot how many hours per year we're going to experience these conditions and require cooling. And then the next two sets of data refer to, firstly, the 30 kilowatt adiabatic unit that you've seen in the picture, where we compare it to the legacy 30 kilowatt DX system. So clearly, when the air temperature is below 15 degrees C, both systems are running on free cooling. So we're just using fresh air to go into the space to provide the cooling required. And we can see the absorbed power for each unit on looking at the middle column. And they're not that dissimilar. And you would expect to see that. There are slight changes, with the absorbed power being 1.589 for the adiabatic unit, again, where we're just bypassing that damper and mixing fresh air with circulating air, as opposed to 2.45 kilowatts for the legacy equipment. And we've got some savings there by having a more efficient fan motor, a more efficient fan blade. But the change really happens when we see our ambient temperature rising into a scenario where we require cooling. So when we're above 20 degrees C, we see in the adiabatic unit, the adiabatic system kick in. So that damper closes and we force the air through the adiabatic cooler and we evaporate water into the airflow. Where our absorbed power for the adiabatic unit does go up slightly because we've got an increased fan power that's going to be required to force the air over that evaporative matrix. But when we compare that to the legacy piece of equipment, when the direct expansion refrigeration system kicks in, you're drawing 23 kilowatts. So there's a huge difference between 23 kilowatts and 1.66 kilowatts. And when you calculate the cumulative effect of the run hours between the 30 kilowatts free air and direct expansion unit as opposed to the 30 kilowatt adiabatic unit, you can see the annual energy consumption for the legacy unit being 70,814 kilowatts, as opposed to 14,088 kilowatts for the adiabatic unit. It's a huge, huge reduction in energy. And this table shows you when you're going to experience it. I mean, it's clearly when we're experiencing the higher temperatures, and the legacy equipment would have to turn the direct expansion system on. So at the side we have the kilowatts per year, and we along the bottom here we have the ambient temperatures. And of course, they're not that dissimilar when we see ambience below 20 degrees C. But as soon as we see that increase in ambient temperature, then the power draw goes up dramatically. And of course, we don't see that with the adiabatic unit. So in this instance, the energy reduction was 80%. Now, 80% reduction in energy is just huge. And there are now literally hundreds of these units out there. It's a very, very successful project. But that was using direct adiabatic cooling. Well, what if we've got a situation where we don't want the relative humidity to increase, but we want to utilize evaporative cooling? Well, in that instance, we have to have a different air handling unit strategy. Then we have to go for an indirect evaporative cooling strategy. So with an indirect evaporative cooling strategy, we have to use a heat exchanger. And what we do is we take our fresh air and we run it through an adiabatic humidifier and we cool that fresh air. And we'll take that line of enthalpy right up as close as we can to saturation. We'll evaporate as much moisture as we can. So we'll increasing our moisture content to the maximum potential. We'll be decreasing the temperature to its maximum potential. But of course, we don't want the relative humidity in the space to increase. So we use the heat exchanger like we would a coil. So we put that cool air through the heat exchanger and we just exhaust it. So we then have our return air coming from our space, going over the heat exchanger, cooling the air sensibly, and then going into our supply air. It's just like, as I say, taking the air out of a space, running it over a cooling coil and taking it back. But instead of using a chilled water supply to cool that coil, we're using an evaporatively cooled air supply to cool that heat exchanger. So in an application where you don't want the air streams to mix, something like a secured building, this is ideal. And the volume of cooling can be increased by circulating more air. And of course, there's no moisture addition. You're only utilizing the sensible cooling that we've achieved by cooling the air that's on one side of the heat exchanger and then using the sensible cooling of that to cool the circulating air. So again, you're not limited to any air extraction or fresh air rate. Of course, though, the volume of cooling will depend on the efficiency of the heat exchanger or the heat recovery unit. So now we're going to look at a case study that utilizes indirect evaporative cooling. This project was the Cork Internet Exchange in Ireland, and it was designed and manufactured and supplied by an air handling unit company in Ireland called EDPAC. And the objective was to provide cooling to a newly built data hall using air-to-air and evaporative cooling technologies only. They didn't want any direct expansion cooling, so no chillers, no additional mechanical cooling. So how did they achieve this? So this is quite a complicated schematic of the air handling unit that was designed for the data hall. And I'll take you through stage by stage what's happening on this system. First thing you need to know is that if you draw a line down the middle of the unit, that is the center line, and each side is the mirror image of the other. So there are 4 circuits of airflow from this system. And the principle is that air is drawn in from external ambience. It goes through an evaporative humidifier or evaporative cooler, where of course we evaporate water into the air, subsequently increasing the relative humidity, increasing the moisture content, but decreasing the dry bulb temperature. And that goes into a mixing area where it can be mixed with exhaust air dependent on the controls. So that cooled air then goes down through a damper and then over a pair of heat exchangers. It comes down over this heat exchanger, then over this heat exchanger, and cools those heat exchangers, and then is exhausted up through this this duct, or indeed is taken back into the mixing area, depending on the temperature requirements in the space. And the same is happening on the other side. Air is coming through the evaporative cooler, is mixing, or indeed not mixing, depending on whether the controls are calling for that, goes through a damper and then goes through the first right-hand heat exchanger, and then goes through the second right-hand heat exchanger, and then goes up and is either exhausted or mixed. So you've got these 2 constant circulating systems. Same on this side, coming in, cooled, going over those heat exchangers and exhausted. In, cooled, cooled again, and then exhausted. And then the other side of those heat exchangers, we've got air coming from the hot aisle, and it's coming up through a main fan, and it's split left and right. On the left circuit goes over the first heat exchanger where it's cooled, then over the second heat exchanger where it's further cooled. And again, it's only sensible cooling because the 2 air streams don't mix. And that then goes back to the cold aisle, picks up its heat gain from the service, back to the hot aisle, over the cooled heat exchanger, over the second cooled heat exchanger, and round. And the same on the other side. We've got air coming from the mixing area, circulating round, that's cooling these heat exchangers. So we've got air from the hot aisle coming up over this first cooled heat exchanger, over the second, and then going back to the cold aisle. I like to explain this like that first, because when we draw the action lines in, it can get a little bit well, a little bit busy. But here you can see that cooled air is going over those heat exchangers and cooling them, and then air is circulating from the hot aisle over those cooled heat exchangers and circulating around. And it's doing this again on both sides. So again, it's just like having drawing the air from a space, having a cooling coil, putting the air over that cooling coil and putting it back in. But instead of the chilled water being your cooling medium, here we're using humidified, evaporatively cooled air. So this is what the system looked like. And just for scale, here's a pair of step ladders that you can see in the photograph, just to give you an idea of how big these units are. And air is drawn up from the hot aisle, from this section here, going up through the fan. It's split, goes left and right, over the first heat exchanger, over the second heat exchanger, and then goes back down into the cold aisle and then circulates back round. And on the cooling side, air comes in through the evaporative humidifier, over the first heat exchanger and over the second heat exchanger, and then circulates round or is exhausted, and we constantly going around like that. And on the other side, it's exactly the same. We've got air coming up from the hot aisle, going over the first heat exchanger, over the second heat exchanger, back down to the cold aisle, and circulating around. But cooling these heat exchangers, of course, on the other side is just the same. It's evaporatively cooled air that's coming down over the first heat exchanger, over the second heat exchanger, and then back up and is either exhausting or mixing. And here you can see some more shots of that air handling in it. It really was quite an impressive machine. When we looked at power demand for the unit, power demand, we were, of course, utilising free air cooling, fresh air cooling whenever possible. So when ambients were lower, we got a sensible, moderate power demand in kilowatts because we were just running the fans. When we get up to the higher temperatures and we start diverting air through those evaporative coolers, we see our power demand increase. But this graph looks quite bad. But when you look at the power demand here at maximum cooling, you're up at just over 25 kilowatts, but you're actually delivering 400 kilowatts of cooling. It's a huge amount of cooling for the energy input. So this project, there were actually 400 kilowatts units installed above the data halls. The return air was 40 degrees C coming up from the hot aisle, and the supply air was 26 degrees C, and the heat exchanger efficiency is 80%. And the electrical consumption per 400 kilowatt module was between 11 and 25, with an annual average of 12 kilowatts. So that gave a power utilization efficiency of less than 1.4. There was a huge amount of savings as when we compare that against the legacy equipment that was providing the cooling for the application. And in fact, the energy was reduced by 75% in this application. Again, enormous amount of energy saved. Again, by using indirect evaporative cooling. Now, you may have an application where we require a large amount of fresh air, but still want to use evaporative cooling. When you come across that application, we then switch to exhaust air evaporative cooling. We still want to utilize evaporative cooling, but again, we've got a high air exchange rate. We don't want those high humidities either. So to do that, we have return air coming from the space, as through a filter, and then we put that return air through a humidifier or evaporative cooler. And again, we evaporate moisture into the air, increasing the relative humidity, increasing the moisture content, but decreasing the dry bulb temperature. We then put that over our heat exchanger. So we evaporate as much moisture into the air as we can. So we've probably taken that down from 26 to 19, something along those lines. And then we exhaust that air. So we're cooling, again, one side of a heat recovery unit or a heat exchanger. So our fresh air then comes onto the heat recovery unit, is cooled and goes to our supply air. And there are, of course, benefits and limitations. So cooling capacity is not dependent on the external conditions and can be used in humid climates. Limitations, cooling limited by air exchange rate and efficiencies of the heat recovery unit. Of course, it's the same whenever we're utilizing a heat recovery unit. And you're also going to need some traditional mechanical cooling. Typically, a situation like this satisfies somewhere between 40 and 50% of your mechanical cooling. Again, this is where we require large amounts of fresh air into the space. So this case study that utilizes exhaust air evaporative cooling is the Mover factory in Germany, and the objective was to provide pre-cooling across 3 air handling units with evaporative humidifiers to reduce the overall mechanical cooling load and its associated operating costs. So how this was achieved is that we took extract air from the factory floor that had a return condition of 24 degrees C and a maximum of 60% RH. That air was then put through the Condair evaporative media humidifier, where again we're evaporating water off the surface of the wetted media, and we're seeing that subsequent increase in relative humidity, increase in moisture content, but decreasing dry bulb temperature as we're sucking the heat energy out of the air. So giving us a resultant condition of 18.9 degrees C at 96% RH. So we then use that air at 18.9 degrees C to cool a heat exchanger or a heat recovery unit, as we saw in the model. And the efficiency was around 70%. So we're then using that to cool our outdoor air. Of course, it won't do all of our cooling, so we have some additional cooling, and in this case we're showing a heating just in case that's required in the winter, and that goes to our supply air, giving us 18 to 20 degrees C. So in this case, the operating hours were 8,760 hours per year. The evaporative cooling operating hours per year, so this is when we were able to evaporate water into the air, so i.e. humidities weren't too high to do it, were 533 hours. The airflow was 53,000 meters cubed per hour, and the total cooling per year for the factory was 63,477 kilowatts. But by splitting the cooling by some mechanical, some evaporative, and some little bit of heat recovery, we could reduce that, and we could do 26,447 kilowatts of the total cooling by the evaporative system. So that gave us a tremendous reduction in energy requirement. And you can see when this happens, and you've seen this before, it's when we get the opportunity to utilize evaporative cooling when the ambients are higher. Again, we can't do all of our cooling. We've got some mechanical cooling, and you can see the mechanical cooling in this chart in the dark blue, starting in June, July, August, and September. But the evaporative cooling shown in the light blue, and a small amount of heat recovery that we're able to do as well. So again, our mechanical cooling delivered was 63,447 kilowatts required, And that has an energy consumption of 19,043 kilowatts. When we were splitting that load by mechanical, evaporative, and heat recovery, because the evaporative cooling energy consumption was so low, to give those 26,447 kilowatts of evaporative cooling, and only an energy input of 497 kilowatts. And of course, our heat recovery is costing us nothing. So our energy consumption has dropped from 19,043 kilowatts to 10,554 kilowatts. It's a huge reduction in energy. In fact, it was 45% less energy that's required in that application. So there are various means of doing evaporative cooling, and each application lends itself to a different specific strategy. So that leads us on to the technologies that are required to deliver this sort of cooling. And the first technology that we're going to look at is an evaporative media humidifier, and it is the most common, most popular type of evaporative cooling system. So how it works is it's built to match the internal dimensions of an air handling unit, and indeed this study is showing just one unit, but you can have multiple units of various different designs. And these things can start as low as 30 kilowatts, but can go up to, you know, hundreds, 400, 500, 600 kilowatts, liters of water that we're evaporating. So they can be absolutely huge and with multiple systems. So air is pushed through this glass fiber matrix. There's a water supply that's supplying water to a tank at the bottom of the unit. The level is controlled by a hydraulic module, and when we get a demand signal from the panel, one or a number of these small pumps will run and will pump water up through these lines to an encapsulated spray bar at the top of the unit. Water then cascades and soaks this glass fiber material, and a proportion of that water will be evaporated off, giving you your subsequent evaporative cooling, i.e. that we are evaporating water into the air, increasing relative humidity, increasing moisture content, but decreasing dry bulb temperature. Now, the really interesting thing about these units is that we don't need water, typically don't need water treatment, because even though we're evaporating water off, we're flushing more water over this material than we're evaporating. So any minerals in the air get washed back down into the tank. Then we've just got to control the mineral content in that tank. So we have a dilution cycle drain that's either done on conductivity or a times drain, depending on the system. So we know we're always going to have good clean water in that tank. We also have a submerged UV light that helps to kill any bacteria that's in the system. But actually we don't want any bacteria in there anyway. And how we combat that is by not having any stagnant water in this system. So if we don't see a demand signal for a certain number of period of time, then we drain the system down, and we've got the UV system there, and there's no water carryover. So you can use mains water in these systems very happily. And again, you can get high humidity outputs out of these. The smallest is 30 kilos an hour, but multiple systems will go up, you know, as big as your imagination will let you, just by using multiple tanks and multiple hydraulic units and multiple media cassettes. They are low energy input. Typically, you've got 280 watts energy input going into the panel and running those pumps. So you can imagine the amount of cooling that you're able to get. There's low maintenance. It does have to fit in with the water management system of the building, and in the UK here that calls for chlorination once every 6 months. Again, there's no water treatment required. Mains, potable or wholesome water is ideal for these units. And next, there's no evaporation distance. When air leaves the surface of this media, the water is evaporated, so it's in its gaseous phase. So there's no water droplets. There's no distance required in your air handling unit that you need to allow for that water to evaporate. It's all done from the air on to the air off side of the cassette. But with that, you don't need a wet section. So your air handling unit can be of standard material. It doesn't need to be stainless steel. We do have to be aware of face velocities. Now, a standard unit will take a face velocity of 3.5 meters a second, and with an eliminator on the front, we can go up to a velocity of 4.5 meters a second. Now, very typically, cooling coils, etc., in air handling units are sized on 2.5 meters a second, so you'd imagine that you wouldn't have a problem. But you have to remember that we have the dimensions of the tank and any blanking off around the side of the unit that is going to increase that velocity because we force more air through a smaller orifice, i.e. the face of the evaporative material. So on smaller units, face velocity can be a consideration. The other consideration is controllability. So for this system to modulate, we need to either turn on or off a number or the singular of these pumps. So we're either wetting one or a number of these lines of cassettes on the system. So really our controllability is going to be plus or minus 10% RH. And the majority of cooling applications, that's going to be absolutely fine. But if you want closer control than that, or indeed you want to humidify in the winter and utilize the system for humidification and you want closer control, then you would look at a different type of system. Then you would look at a high pressure spray system. Now a high pressure spray system is working in a completely different way. Firstly, we're spraying water into the airflow. And whenever we're spraying water into the airflow, we have to use reverse osmosis treated water. Now, a reverse osmosis unit is going to take a vast majority, 97–98% of the minerals out of the water before we spray it into the air. We have to do that for two reasons. Firstly, if we don't, the nozzles that you're using will block up. And secondly, any minerals that get sprayed into the air handling unit will fall out into the air handling unit as the water changes its state from a liquid into a gas. So we have to use RO water. So here you can see an RO plant with a high pressure pump and a control panel. Water is pumped to a series of control valves that are linked to these different spray bars. And on each spray bar is a number of different nozzles with different capacities. And we spray that water into the air handling unit where it evaporates and we get the subsequent cooling or humidification. But by having a number of these different spray bars with different capacity nozzles, it gives us the ability to modulate the output to a closer control. So typically a high pressure system will give you plus or minus 5% RH control. You can have high humidity outputs and you can run multiple air handling units from a single pump station and controller. So you can have up to 4 air handling units supplied by one plant. So if you've got multiple AHUs in the plant room, it's a really good option. Again, you do need to use RO water, and it is a wet section in the air handling unit, so it should be of a stainless steel or protected construction. And of course, we need to allow for drainage in the air handling unit. And also, we have to have a blade eliminator. The blade eliminator will catch any water droplets that haven't evaporated. So you only have water in its gaseous phase in the air circulation system. And that's okay, that's great. But if you want better controllability than that, and you want to reduce the wastage that you get on a blade eliminator, then you use a system that utilizes both types of technology. You use a hybrid system. And with a hybrid system, again, you're spraying water in its liquid state into the airflow, so we need to use reverse osmosis treated water. So here we have in our schematic a water softener, the base exchange water softener, where we're taking the calcium out and replacing it with sodium. And that extends the life and increases the efficiency of the RO plant. That water then goes to a hygiene unit, and then it goes to an array of nozzles that's mounted inside the air handling unit. And here we have many, many more nozzles in this array. We've got so many nozzles on there that we can have up to 31 stages of control, which gives us a very fine amount of modulation. So it will give you plus or minus 2% RH control, which is fantastic. But after we've evaporated that water, or after a certain period, where we would ordinarily have a blade eliminator, here we have a ceramic matrix. And any water droplets that haven't evaporated will get caught on the ceramic matrix and will be evaporated in the same way that an evaporative humidifier does. It's just using heat energy to change the state of that liquid from a liquid into a gas. So we have a dry section after the ceramic matrix. So this will give you a closer control and reduce the water, and of course it's incredibly hygienic. So when we compare the three technologies, there are 5 things to consider. There's water consumption, energy consumption, pressure drop, control tolerance, and the air handling unit material. When we look at the first system, the evaporative system, that is a low water consumption. Typically, you're going to be using 1.1 to 1.2 times the amount of water that you're going to evaporate as a water consumption. So that's your main water on flush cycles. Energy consumption, less than half a kilowatt. It's very small. You will have, though, a higher pressure drop because you have a thicker evaporative matrix that we're pushing the air through. And our control tolerance is typically plus or minus 10% fresh air, on 100% fresh air. But our air handling unit material can be standard because it isn't a wet section. When we go onto a high pressure system, here we have to use reverse osmosis treated water for the reasons that we spoke about. So we're using more water because for every 100 litres that you put into an RO plant, you'll get roughly 50 litres out the other side when the air on water temperature, where the water on temperature is around 11 degrees C. So if you put 100 litres in, you get 50 litres out. So you get a high degree of wastage. Energy consumption, again, is not a huge consideration for these. It's still under a kilowatt. There is the pressure drop because we're having to push the air over that blade eliminator, but typically around 40 pascals is not uncommon. Our control tolerance, plus or minus 5% RH. But again, really importantly, we've got a wet section in the air handling unit, so the construction should be of stainless steel. When we go to a hybrid system, we get a medium amount of water consumption because we're using that ceramic matrix to catch any water droplets that haven't evaporated. But again, we're using RO water in the first place, so it is higher than the evaporative system. Energy consumption is very similar, less than a kilowatt. And we have got a pressure drop. We've got to get over that ceramic matrix, so we're going to see around 60 pascals. But our control tolerance, again, if we're humidifying in the winter as well, will give us a really good control tolerance of plus minus 2. Again, air handling unit material has to be stainless steel. So finally, there's a really cool tool, actually. It's called MyCoolBlue, and this is an exhaust air simulator for the iPad, and it shows the amount of cooling for an exhaust air evaporative cooling application and provides it as a percentage of the overall cooling needed to reach any desired room condition. And it's based on a live 10-year weather history at over 300 locations around the world, and you can download it for your iPad on mycoolblue.com. I'll give you it's a really nice illustrative tool. Well, we at Condair, we design, manufacture, install, commission, service, site surveys, risk assessments. Of course, we do both humidification, dehumidification, and evaporative coolers. And once again, thank you so much for attending the webinar. I really, really appreciate it. I'd like to hand it over now to see if you have any questions.
Well, yeah, you certainly certainly kept me very busy, those questions.
Fantastic.
Right, okay. Okay, so what have we got here? Question 1. Yeah, I've been asked this a number of times. Legionella. Legionella in the water, how do the units combat that?
Yeah, that's a really good question. So firstly, we need to understand a little bit about Legionnaire's disease. For you to catch Legionnaire's disease, you need to breathe in a water droplet that contains the live bacteria Legionella pneumophila. So first of all, if an evaporative system is used, there is no water carryover because that bacteria only exists in water. It doesn't exist in water in its gaseous phase. So with an evaporative system, there's no water carryover, so you can't get it. But actually, we don't want Legionella or bacteria in our system at all. So again, we combat that first in the evaporative system by having no stagnant water. When we don't have a situation, or when we have a situation where there's no demand signal, the unit will, after a period of hours, the unit will drain down. We've got constant water movement. So Legionella and bacteria likes to breed in stagnant water. So we don't have any stagnant water in that tank. So water's constantly moving. And we have a submerged UV light. So any water that travels over that matrix, it comes into contact with the UV light, and that has a really, really high kill rate. And of course, with an evaporative system, there's no transition method. With the other units, we're using RO water, so it's coming from a clean, wholesome supply, and it's going through an RO plant, and then through a silver ion exchange. So that water is then clean and it's being sprayed into the air handling unit. And again, there are many hygiene routines built into the software of these units that will purge water out, so there's no stagnation in the lines, and we have those inline hygiene systems, so we don't get any bacterial growth within the system.
Brilliant, thanks, great, Dave. Question number 2 is regards to water and the cost of water. Basically, people are asking, has the cost of water been taken into consideration, and also where water is scarce, should that be shouldn't water usage be taken into consideration too?
Yeah, it absolutely should. Now, we're very fortunate here in the UK that we have an abundant water supply, an abundant, clean, wholesome water supply. So water supply typically for us costs around a penny a litre when you put in the cost for supply and the cost for drainage. So of course that should be added into the running costs. We haven't looked at it today because it does vary between the systems. With a system that is utilising an evaporative system, our water usage and our water cost is going to be lower because we haven't got as much water that's going through the RO plant into a drain. Whereas the cost of the water, of course, when we're using a spray system and it's going through an RO plant, we mentioned that we're using twice as much water. And it's really interesting when you say, what if water is scarce? Yeah, of course. I mean, if your water is coming from a desalination plant or something like that, then the cost of that water is a big consideration. So, of course, that needs to go into your calculations, and it will depend globally what the water availability is wherever you are geographically located.
Brilliant. Thanks, Dave. Question number 3. We've had lots of questions. So what we'll do is, any questions you can't get to today, we'll come back to you via email. Well, question number 1 is, how does the temperature of water affect the cooling capacity of the direct adiabatic cooling unit?
Yeah, this is a really interesting question, and I've been asked it a number of times because there's an assumption that if we heat the water up, do we get more cooling out of it? Or if the water's cooler, do we get more cooling out of it? Well, actually, it doesn't make a huge amount of difference because the vast amount of energy that's taken out of the water happens as the water changes its state. So it's the change of state of the liquid that is taking the energy out of the air, not necessarily the temperature of the water. So the temperature of the water, really, we don't want water supply temperatures over 11, 12 degrees, certainly here in the UK. So standard water mains temperature. Because of course, if you're storing water at a higher temperature, then you have more risk of bacterial growth. So ideally for us, mains water supply temperature is ideal, and the temperature of the water doesn't make a huge amount of difference to the amount of cooling that you're going to get, because the cooling is derived from the change of state of the liquid, not the change in temperature.
Great, thanks, Dave. And last question for you today. How close to the saturation line can you get with an adiabatic cooler? What percentage?
That's a really interesting question as well. Now, there's no such thing as a 100% efficient machine, and the humidifiers are no different. Typically, you'll get up to 97, maybe 98% of the travel line of the line of enthalpy. So typically, you'll never be able to get to 100% saturation by evaporating water. You'd only do that by getting steam, and of course that will be completely counterintuitive to what we're doing. So in this instance, you may be able to get up to 96, 97% efficiency. So pretty close to saturation, but not to saturation.
Great, Dave. Well, like I say, I've got loads more questions. I think here for another hour, but I think that's a good place to wrap up at this point. But yeah, thanks very much, guys, for your questions. Very good ones.
Great. Again, thank you all so much for attending the webinar. And again, we at Condair, we only supply the evaporative cooling elements of these systems. We don't supply the air handling units or the different construction machines that you've seen today. We only supply the evaporative cooling products. Again, if you do have an evaporative cooling application or a dehumidification application or a humidification application, please feel free to drop us a line or give us a call or check out our website, www.condair.co.uk. Thank you very much, everybody. Have a great day.
Thank you. Cheers. Bye.